We will continue with the lecture on bituminous materials, and we have looked at some of the properties of bitumen and how bitumen and asphalt interact. Now we will go on to see how, wait, I will start again. Well, it is okay. We will now continue with the lecture on bituminous materials. We have looked at how bitumen and aggregates interact, how bitumen behaves under different environmental conditions, and now we will go on to see how asphalt concrete is used and what can affect the mechanical properties and the long term behavior of asphalt concrete. On this leader slide, I have the taxiway of the Singapore Changi Airport. It is one of the busiest in the world, and this has several taxiways and runways with asphalt concrete as the top layer, and this is very typical of many airports. And we see that asphalt now is not only suitable for roads and pavements, but also it can take much heavier loads that we can encounter in an airport or in a port stockyard and so on. Asphalt pavements have a long history. Asphalt pavements as we know them today have been around for almost 200 years. Mastic was used for footpaths in Paris in 1837, later on in the 1860s asphalt as such started to be used in London and in New York. Later again we have a lot of applications which occurred in Europe and in the United States with different types of asphalt. What are the typical elements of asphalt pavements? First we have the subgrade, which is the existing soil or the ground over which the pavement has to be built. If the soil does not have a good ability to carry the traffic loads, that is repeated normal loads coming from traffic, then it has to be stabilized or improved to get what is called a good resilient modulus. The resilient modulus is the ability to carry loads. On top of this subgrade, generally you will have a sub-base grade, sub-base course, and this is made with material superior to the subgrade. If the subgrade is good enough, that is it has a high enough resilient modulus, then it is not necessary to have a sub-base course. The base course can be directly laid on the subgrade. So, on top of the sub-base course, we have the base course. The base course could be an asphalt concrete, it could be a Portland cement concrete, or it could be granular material. It could be granular material treated or untreated. So, this is compacted well, and on top of it the wearing course is laid. In some cases the granular material can be treated such that it also provides for drainage, so that there is no water stagnation under the surface course, which can lead to the failure of the surface course eventually. So, if there is a stagnation of water in the area that the pavement is going to be built, it is a good idea to have a base course which can allow drainage and prevent water from stagnating under the surface course. So, finally, we have the top layer which is called the surface course, and this is the layer that we see in a pavement after the pavement construction has been completed. And in our context we are talking about an asphalt layer capable of withstanding wear and abrasion due to the vehicle traffic, that is it has to survive well during its intended life under the traffic that it has been designed for, and it should be stable, that is it should continue to be smooth, usable over a period of time. It should not develop undulations and cracks and so on. So, ideally these are the typical elements of an asphalt pavement, and we will see some typical cases of the cross section of pavements in the next few slides. So, as we look at typical sections, first we will see the case of a full depth pavement, where we have the prepared subgrade with a sufficient resilient modulus. On top of it we have the asphalt base course. So, this could be the asphalt concrete, or it could be granular material treated with asphalt, so that we get a good enough base course, and on top of that we have the asphalt surface. We have the asphalt concrete surface at the top. Then we could have a case of asphalt pavements with untreated base and sub base. So, we have the subgrade prepared to have the adequate resilient modulus. On top of this we have the sub base, which is granular material in this case, or soil not treated. Then on top of it we have the base course, which is again granular material untreated, but sometimes it could be treated with something other than asphalt on top. And then finally we have the asphalt surface right on top, which is the surface course. Now, in some cases you can avoid the sub base if the subgrade is good enough, then we can have directly the base and then the surface course. We can also have sections of asphalt pavements with cement concrete or combined cement concrete and asphalt bases. So, here you would have subgrade, on top of it there is an asphalt concrete layer, above that there is a Portland cement concrete layer which forms the base, and on top of it all we have the asphalt concrete surface. We can avoid in some cases the intermediate asphalt concrete layer as which comes below the Portland cement concrete by having the Portland cement concrete directly in contact with the subgrade. So, here you will just have 3 layers in this section. What are the different types of asphalt mixtures? The most common, and generally this is what we see many times on the streets and roads, is what is called hot mixed asphalt. So, in this case we have bitumen that is heated and mixed with aggregates which are also hot, and this is done to drive off any moisture that could be there in the aggregates, and more importantly to have the bitumen and asphalt sufficiently fluid such that you can have a uniform mix, and during placement a good compaction can be achieved in the asphalt concrete. So, the bitumen is heated say to temperatures of 150 to 180 degrees centigrade, and aggregates are also heated up, the whole thing is mixed together, and in the hot state the material is spread out and compacted as it is cooling. In the case of emulsified bitumen being used as the binder, lower temperatures can be used. Emulsified bitumen is bitumen that is mixed, made into a colloidal suspension with water, having an emulsifying agent that facilitates a stable emulsion. This brings down the temperatures that we need to have in hot mixed asphalt, and also facilitates the fluidity of the asphalt. So, typically this is what we will generally have and use, hot mixed asphalt. There are also other types of asphalt mixtures which are being more commonly used in some countries and probably will come into practice in other places as well. Warm asphalt mixtures are similar to the hot mixed asphalt, but the temperatures required for mixing and placing are lower by up to 30% less than the temperatures needed for conventional hot mixed asphalt. This lowering of the temperature, which is convenient because you need now less energy, it is you can work at temperatures close to ambient temperatures, is achieved by using two binders instead of one. First, a softer binder which does not require now very high temperatures to make it soft enough is first mixed with the aggregates. This coats the aggregates and is adsorbed into the surface of the aggregates, and later during the mixing a harder bitumen is added, which now binds the aggregates together and gives the asphalt concrete a body. Also, very often additives are used to increase the fluidity of the warm asphalt mixture. Examples of the additives used are zeolites that entrain air and paraffin, which facilitates the fluidity. So, here as I mentioned earlier, we have warm asphalt mixtures which are similar to hot mixed asphalt, but can be worked at lower temperatures. Now, another type of material which is coming into practice and is being used to some extent is cold mix asphalt. Cold mix asphalt means that we can mix the asphalt and place and compact at normal temperatures. There is no heating required in the asphalt at all. So, here the mixture of asphalt is made with liquid bitumen or foamed bitumen as the binder. Liquid bitumen could be emulsified, which I just mentioned, where we have bitumen and water in an emulsion form. This is kept stable by the use of an emulsifying agent, or we can have cut back bitumen. Cut back bitumen is where bitumen is dissolved in a solvent, and that again facilitates the fluidity of the bitumen, and in both cases the evaporation of the water in the first case and the solvent in the second case allows the bitumen to settle and bond and give the asphalt concrete the matrix that it requires. The other option in cold mix asphalt is to use foamed bitumen as the binder. Foamed bitumen is where steam bubbles are formed inside the bitumen, so that the bitumen becomes very fluid because of these bubbles of steam and the presence of water, and this facilitates the mixing and the placing of the asphalt at normal temperatures. So, the big advantage of cold mix asphalt is that it can be mixed and laid at ambient temperatures. Additives are very commonly used to improve the bonding between the asphalt and the aggregates, because we do not have the high temperature like we had in the case of the hot mix asphalt that facilitated this bonding. Here what happens is that the mixture of the cold mix asphalt has enough water to form a thin film around the aggregates, and as the bitumen particles are dispersed in this water, the droplets now spread in this film of water that is around the aggregates and reach all the different surfaces that have to be wetted. However, since there is a lot of water in the cold mix asphalt, as the water evaporates it leaves behind air voids. So, there is a relatively high air void content in cold mixed asphalt. There is a relatively high air void content in the cold mixed asphalt once the water has evaporation and the compaction is complete. Sometimes to remove this water faster and also to bind the water, instead of having it stay inside the asphalt, a small amount of cement is added which hydrates and combines with this water, thereby accelerating the curing of the asphalt itself and not having delays in the curing due to the presence of water. So, these are the different types of asphalt mixtures. The most common, as I mentioned earlier, is the hot mixed asphalt. Let us look at the mechanical behavior of asphalt concrete. There are different aspects which are important, and then we will go on to see what happens when we do not have good mechanical behavior and durability. First, we have to understand the concept of stability. We talked about the surface course being stable. What does this stability mean? Stability is the property of the asphalt concrete to resist permanent deformations under traffic loading. That means, it should not undergo significant plastic deformation as time goes on under traffic. It should remain plain, it should remain integral and not become bumpy or undulating with time. This stability is best maximum when you have an asphalt concrete mix with dense graded aggregates. Remember, we had talked about grading in the previous half of this lecture. Dense grading means there is very little voids, the aggregates are in contact with each other and load is transferred through the aggregate skeleton. The bitumen content is also minimum and there is basically an interlock between the aggregates. The voids, however, are filled with bitumen. In this case, we will have good stability in the asphalt concrete. We also have to look at the concept of flexibility. Flexibility is the ability of the asphalt concrete to conform, to follow, to adapt to minor long term settlement of the base layers beneath the asphalt concrete without cracking. Suppose there is the subsidence of the subgrade, subbase or base layer a little bit. We do not want a hollow space to form under the asphalt concrete, which will eventually lead to a depression on the asphalt concrete or a sudden cracking or failure. We want the pavement to be flexible to such settlement, and that is why asphalt concrete pavements are called flexible pavements. This ability to adapt to small settlements of the base layers is important, otherwise it becomes very difficult to have a perfect base layer and not have cracking. This flexibility is now higher for open graded aggregates, that is, there is a lot of space between the aggregate and a high bitumen content, because bitumen is what is giving the flexibility, it is giving the ability of the asphalt concrete to adapt to large deformations. Now, you can clearly understand that stability and flexibility are competing aspects. We have to have a good compromise between stability and flexibility. We always need good flexibility, but we always want good stability with sufficient amount of flexibility. That way we will have a surface that does not become undulating with time, can take traffic as it should without bumpiness and roughness and disturbance to the comfort while driving, as well as not have cracks whenever there is a small settlement of the base layers. So, stability and flexibility both have to be taken into account, and we find that the mechanisms which give these two are also different. In the first case, when you want something stable, you want very few voids, we want the aggregates to be touching each other, very dense grading, very compact concrete. However, if we have the same thing when we look at flexibility, we will find that the flexibility will be very low. For something to be very flexible, we do not want the aggregates to touch each other, we want a cushion of bitumen between the aggregates, and therefore, we need a high bitumen content. So, there is a compromise needed between these two. So, we need a certain amount of bitumen and we have to fill all the voids. However, we cannot have a lot of flexibility because that will lead to a bumpy or undulating pavement. Other than this, we also have to worry about the fatigue resistance. Fatigue, as we already looked at, is the ability to survive traffic that is cyclic. Repeated traffic, repeated loading can cause fatigue, which can lead to cracking and malfunctioning of the surface. We find that mixtures with higher bitumen contents and densely graded aggregates have better fatigue resistance. So, there is some amount of bitumen that is needed. We cannot have all the aggregates so compact that the stiffness is very high and cracks develop. We need some amount of bitumen to facilitate this adaptability to fatigue loading that can prevent cracking from occurring. When we talk about cracks, we have to also understand that there is a crack resistance of asphalt which is acting to prevent cracking from occurring. This is the tensile strength or the maximum tensile stress that the concrete can take. This depends on the properties of the bitumen, the quality of the bitumen aggregate bond, the amount of bitumen and the voids content of the asphalt concrete mixture. So, all these will influence the tensile strength of the asphalt concrete. At rapid loading rates, low temperatures, the tensile strength of the concrete is reasonably high. It is in the range of 4 to 10 megapascals. At slower loading rates, higher temperatures, the tensile strength will drop, because bitumen, the strength of the bitumen will also decrease. Another very important aspect of a road surface is the skid resistance. Skid resistance influences the distance of braking and also the ability to ride on a road surface when the surface can be wet. And this skid resistance is provided in the asphalt concrete by exposed aggregates, the roughness provided by the aggregates and their surface texture. So, in order to have this, we need to have some aggregates exposed on the surface. We need to have aggregates that are rough enough. We cannot have something like smooth pebbles over which a car tire can slide. We also cannot have aggregates that break very easily due to the repeated traffic loading. So, we need strong rough aggregates that can be exposed on the surface, and this will give skid resistance and braking resistance. Over the long term, something that we see very often in asphalt surfaces is that there is permanent deformation. What is initially a plain flat surface does not remain so. One reason could be the settlement of the base, but other than that we can have plastic deformation of the asphalt itself. Here the traffic produces normal and shear stresses, and this can lead to plastic deformation. Rutting is the most common form of plastic deformation. Rutting is where you have a ditch formed along the direction of traffic where the tires normally go, and this ditch becomes deeper and deeper, and some of the asphalt is piled on to the sides of the ditch. That is called rutting. I will show you a picture in a few minutes. Both cracking and rutting that we have talked about depend on the ambient temperature of the pavement, or consequently the temperature of the asphalt concrete. Here we have a graph showing viscosity on the y axis and temperature on the x axis, and we see that viscosity decreases with increase in temperature, and this could give rise to susceptibility to temperature, that is, there is significant change in the stiffness and flexibility or viscosity with temperature, and this affects the performance of the asphalt pavement. we find that in general an asphalt pavement is more susceptible to cracking at lower temperatures and rutting at higher temperatures, because at lower temperatures what happens, the stiffness increases, it the material becomes harder, and when there is some subsidence of the subbase or fatigue induced stresses, there can be cracks that can be developing at lower temperatures. Now at higher temperatures what happens, the viscosity decreases, the material becomes more flexible, and due to traffic there can be plastic deformations occurring and resulting in rutting. So to ideally have less temperature susceptibility, we should decrease or have the lowest possible viscosity at lower temperatures, and we should have higher viscosity at higher temperatures, because viscosity is what is governing rutting. So if we want less rutting, the viscosity at higher temperatures should be higher. On the other hand, when we have low temperatures, viscosity helps, in the sense that a material that is more fluid will have less cracking ability, or I will repeat this, at lower temperatures a lower viscosity helps, because a lower viscosity decreases the possibility of cracking, it adapts to the fatigue stresses and possible subsidence of the subbase, and you can have less cracking occurring, which becomes a problem at lower temperatures. Now other than the mechanical loading, we can have deterioration in the asphalt concrete due to aging and stripping. What is aging? Aging is where the bitumen under service conditions after a long period of time becomes harder and less ductile, it becomes stiffer, and this occurs due to changes in the structure and the composition. There is some oxidation of the resins, the volatile substances are evaporated, and the faster this occurs, the rate of hardening is higher, and the aging process becomes worse when we have higher temperatures and when we have very heavy sunshine, say in a desert condition, and you do not have any tree shades and so on, because there is more ultraviolet radiation and this affects the aging. So this limits the age until which we can use asphalt surface due to the aging of the bitumen and consequently that of the asphalt concrete. Another aspect which affects durability is what is called stripping, where the bitumen surface on the aggregate is stripped off, it is removed because the bond between the bitumen and the aggregate breaks down, and this occurs due to a combination of traffic, weathering and moisture presence. Weathering is what we saw earlier and what we called earlier as aging. So that gives rise to weathering. Then when water is also present, this water is forced in to the asphalt concrete due to the action of traffic, and this results in the separation of the aggregates from the bitumen matrix, and this leads to potholes and raveling of the aggregates or the loose aggregates coming off from the surface. These are some pictures showing the distress that can occur on pavement surfaces. Due to very high plasticity or plastic deformation on the surface, we can have something called shoving, where you see that there is an undulation formed because of some traffic, say due to turning conditions. Here you have shear stresses which push the asphalt to one side, forming a ditch in some areas. This is called shoving. Then we have something more common, which is rutting, where we have the tires always following a certain path along the length of the asphalt, and at higher temperatures or high bitumen contents, inadequate mix design, we can have a ditch now forming along the length of the road where the tires have been travelling, and there is a pile up of asphalt on the sides of this ditch or rut. It can be local or it can be over a long distance like we see here, and this, as we saw, becomes worse at higher temperatures and when the viscosity is lower. The best way to avoid this is to have something that is more stable, dense packing, very low bitumen content filling up all the voids. On the other hand, we can have cracking occurring when the viscosity is too high, that there is not enough flexibility in the pavement to adapt to the stresses that cause cracking. This occurs very much when the temperatures are low, and it can be made worse when we have subgrade settlement. So, when there is, say, the subgrade slowly settling along this section, if the viscosity is so high or the stability is so good that it cannot adapt to this subsidence, then a crack develops, because under the asphalt concrete there is no support. So, a crack can develop, and this can have pattern type cracking or single cracks. You can also have, at low temperatures and poor mixed design, this pattern type cracking. You have lot of cracks that develop along the length of the pavement, and when these cracks join, a pothole develops. A piece of the asphalt concrete comes off due to traffic movement and a pothole starts, and this develops further and further as the aggregates and the binder come off and water is driven in by traffic and rains into the asphalt concrete. So, these are different problems that have to be avoided. They can be avoided through proper mix design and also maintenance. Asphalt concrete is a surface that has to be maintained well, has to be inspected and repaired, so that small damage does not develop into major deterioration in time. Now, we saw that water is harmful to asphalt concrete because it can lead to cracking, it can lead to pothole formation, deterioration of the asphalt concrete in general. Permeability is what governs how much water and air can enter into any material. So, permeability is also important for asphalt because it controls the extent to which air can enter into the concrete and water can enter into the concrete. The exposure of the air is bad because it leads to the hardening or aging of the bitumen and consequently that of the concrete. Then the entry of air, as we discussed earlier, leads to deterioration. It can lead to stripping, it can lead to failure of the sub base. The water entering can remove some part of the sub base, and consequently the asphalt concrete deteriorates, and on the micro level the bitumen aggregate bond also deteriorates. So, permeability, as in cement concrete, is a good measure of durability in asphalt concrete also. Permeability is governed by the void structure, because permeability means that the air and water can move through the asphalt concrete. This is usually through the void structure. So, permeability is controlled by the volume of voids, the void sizes, that is the distribution of the void sizes, and whether the voids are continuous or isolated. More voids, larger voids and continuous voids are bad in terms of permeability. The permeability increases, more water will enter into the bitumen structure. This is a graph from Ilston and Damon showing variations of the permeability coefficient K with void content and binder content. We find that generally permeability is higher for lower bitumen or binder content, that is, here we have 3% binder content, then we have 4, 5, 6%, and we find that for 3% binder content the permeability coefficient is much higher than 4 and so on. So, a lower binder content gives a higher permeability because all the voids are not completely filled and there are some paths for water and air to go through. We also find that permeability changes more when there is a change in void content for higher bitumen content. For example, if you see the case of 6% binder content or 5% binder content, as the voids increase there is a significant increase in the permeability. At very low binder contents the curves are basically flat, there is not much change in the permeability as void structure changes, but when you have more binder, that means now the value of the permeability is lower, but as the voids increase the permeability increases because the water and air move through the binder, not through the aggregates. So, more binder means there is more of a possibility of water going through. Even though the voids are all filled up, there could be some paths for the water to move into the asphalt concrete, and this is facilitated by a higher void ratio, higher amount of space between the aggregates. Let us look a little bit again on the effect of moisture. What happens when moisture enters into the asphalt concrete? At higher temperatures, water now tries to evaporate, a blister forms on the bitumen surface and this blister ruptures due to traffic as temperature increases, and this blister leaves a pit on the surface. This pit develops further, water is now pushed into the pit by the tires and hydraulic scouring occurs, that is now water is pushed into the pit as the tire is approaching the pit, and as it leaves the pit the water is pulled out. So, this repeated action of water being pushed in and out into the pit makes this pit larger, makes the damage worse, and it facilitates the stripping of the aggregates. This thing becomes worse when the asphalt concrete is poorly compacted. There could be water inside, there could be air voids inside, which make things worse when there is hydraulic scouring, when water is present. And what we find that any water that is inside, now due to the pressure of the tires, due to the traffic pressure, the water now migrates to the interface between the bitumen and aggregates. This causes disbonding, the bitumen strips off from the aggregates and the aggregates now are not bonded together, and with time you see the aggregates coming off. This is the reason why after every monsoon in India we find that there is a huge deterioration, or we find that there is a significant deterioration of the asphalt concrete surface due to the combination of rains, high temperatures and traffic. Some of these problems that occur in asphalt concrete can be mitigated by the use of additives and fillers. So, we will see some of the additives and fillers that are normally used. We can have what are called anti-stripping agents. These are organic compounds or inorganic chemicals that migrate to the aggregate bitumen interface and facilitate a good bonding between the aggregate and the bitumen. The bond is now stable because of the presence of these anti-stripping agents. They mitigate the effect of say little bit of water on the surface of the aggregates or some other imperfection on the surface. The anti-stripping agent facilitates better bonding between the aggregate and the bitumen and a stable bond to be developed. Antioxidants are chemicals which prevent aging from occurring very fast. We looked at the different processes that lead to aging. Antioxidants retard the aging process, delay the aging process, so that the asphalt concrete remains more durable for a longer time, we can use it for a longer time. What is becoming very common, is already common in many countries, is polymer modification, where we have polymers such as styrene, butadiene, latex, rubber and other natural synthetic polymers added in asphalt concrete to increase the viscosity, improve the adhesion and retard oxidation. So, the addition of these polymers first of all makes the viscosity higher, that it makes the concrete more sticky. This improves the bonding between the bitumen and the aggregates and between layers of the asphalt concrete pavement, and also retard oxidation like an antioxidant. It increases the life before aging occurs significantly. So, this is called polymer modification and we will certainly hear about it more, and there will be more usage of polymer modified bitumen concretes in the future. What is quite common in most places in India, that we also see the use of stone dust as a filler. What is called quarry dust or crushed fines is used as a filler. This fills the voids, decreases the bitumen content and improves the hardness of the asphalt concrete. It gives a harder surface, and that is the reason why fillers are used, and also fillers are less expensive than the binder and therefore it reduces the cost. One filler that is used both for the filling purpose and also to improve adhesion between the bitumen and the aggregates is calcium hydroxide, hydrated lime. This is also commonly used to get better bonding between the bitumen and the aggregates and to act as a filler in the binder. So, these are some of the additives and fillers that are used in asphalt concrete. So, these are some of the references. There is a lot of literature and there are entire courses which are taught on pavement materials, and here we have given an introduction to asphalt concrete and bitumen, and further reading will help resolve doubts and give more information on asphalt. So, to summarize, we have looked at bitumen and asphalt concrete. This is a very important material as far as pavements are concerned. Bitumen is also used in waterproofing applications, and certainly all of us have seen or driven on asphalt concretes to understand the use, the importance and also the problems that occur when an asphalt concrete is not properly designed or placed or maintained. Thank you.